To Physics Lab 5. For my final lab, I chose to focus on collisions and conservation of momentum. Lab 5 details. The purpose of this lab was to demonstrate the ideas and workings of the conservation of linear momentum, collisions, and how it all relates to Newton's second law. There'll be a final question at the end to question, is all of energy and momentum really conserved? Conclusion. At the conclusion of this lab, it was found that not all of momentum/energy is actually conserved in a real-life situation, as it can be transferred into other forms. Principles and concepts used in this lab were Newton's second law, along with the conservation of momentum. From the conservation of momentum, we know that the change in momentum is equal to zero, which implies that the initial momentum is equal to the final momentum. Another principle that was used in this lab was kinetic energy, which is equal to 1/2 times mass times velocity squared. Another thing used was momentum, which is just equal to mass times velocity, and the velocity update equation for net force. For Newton's law, my bad. So more info and initial and final conditions. So you can see my info here about the system and the surroundings and initial and final velocities. My system was two cars, car 1 and car 2, and the surroundings was nothing. And you can see the rest of the information below. So I'm going to play a quick video to show you all how we analyze the data. As you can see, car 1 hits car 2, and this is the situation we have here. Okay, here are my calculations. So for car 1, it was found that the initial velocity was 0.09 meters per second. The final velocity of car 1 after the collision was 0 meters per second. And the initial momentum was 0.135 kilograms times meters per second, and the final was 0 kilograms times meters per second. And for car 2, initial velocity was 0 meters per second, and initial momentum was also 0 kilograms times meters per second. And the initial momentum of car 2 before the collision was 0 kilograms times meters per second and 0.135 after the collision. And you can look on the right here and you can see I calculated the change in kinetic energy, and that gave me that delta K was equal to 0, and that implied that the systems of car 1 and car 2, it was an not inelastic, but it was an elastic collision in which no energy, no kinetic energy is lost, and that it stays the same. And that is true because this is not modeled as a real world situation, and just like something like to just to test out what a collision would actually be like. Here's my tracker data for car 1 and car 2. You can ignore the part where the curve for car 1 is flat. That was before like the video actually started like showing the car moving from the point where it started at to where it hit car 2. And you can see car 2 on the right here. It has like a pretty kind of curvy graph at the start, and then it starts to plateau out towards the end. Here's the observed data or the data from Excel. We can see that car 1 is exposition data, it increases, and the exposition data for car 2 also increases, and that's because once again we're looking at linear conservation of linear momentum. We're only looking at one-dimensional motion here. There's no motion in a y or z direction, so that's why the y graph is precisely flat. What if? So what if this was a real world situation between two actual cars that crash between each other? So the situation we just looked at, the initial momentum was equal to the final momentum. Well, in a real world situation, the momentum wouldn't just be conserved. The energy and the momentum of the crash would also go into things like drag or friction, and it wouldn't just be conserved between the two cars. And that's because these are dissipative forces, and they irreversibly spread energy away from the system and towards the surroundings, and they do negative work on the system. Thank you for watching, and have a good day.